Hello.
Can you hear me?
I hear you.
Okay, I'm on my cell phone, so just let me know if I'm loud enough. Yes, Randy and I had a very exciting morning, but we're going to do our best to give you this presentation about this project that I'm doing with LSU and about InSAR in general, because I want you to understand the capabilities and the limitations of the technology. So are we on the first slide?
Indeed.
Okay, can you go to the next one? I'll just say next from now on. And sadly, I put in animation, so you're going to hear next a lot. So as you've probably already seen a slide already showing this, there's a lot of problems with land loss in Louisiana, and it boils down to a combination of subsidence, organic and inorganic sediment deficiency, lack of production of organic soil, and also with changes in the sea level. So right now, the latest measurements show that average subsidence across this area is 9 millimeters per year, which is pretty large, and it's much larger in some areas. And that's driving land loss, and it's also because it's occurring so rapidly, it's difficult to track what the elevation of these areas are without making frequent updates, which I was only listening to the last presentation, but it sounded like a great discussion of how updates are going to be done now and in the future. Next. So NASA has a large suite of Earth observing instruments, and some of them can be used to address this problem. I show here, all of the missions that are currently on orbit and working in green, and then in orange, the ones that are coming up relatively soon. And I'm going to focus at the end of my talk on the NISAR mission, which is one that is particularly relevant to InSAR observations of the Earth. So just to kind of, next slide, just to kind of give you an introduction to InSAR and what its capabilities are, I go back 5 years ago to something you might have seen in the news about San Francisco's Millennium Tower being observed to sink from space, and it had sunk 16 inches from when over the 7-year period. The title says, "A photo shows San Francisco's Millennium Tower sinking from space." In fact, it was not a photo. It was a radar image, and it was processed with interferometry with InSAR. It was an image that was taken with the Sentinel-1 spacecraft and instrument, which is operated by the European Space Agency. Next slide. So the data that gave away the hint that there was a problem is shown here. It's a map of deformation versus deformation rate calculated from a time series of images. And that little area that is in the white oval highlights the Millennium Tower. Next. And this is a pretty, what I would call a small signal. I mean, it's consistent and it's across a single building. So there's a lot of reason to believe it. However, after this signal was seen and the European Space Agency provided their results, next slide, please. Tre Altamiro, which is a company based in Italy, got high resolution, very high resolution synthetic aperture radar data, so something like 3 to 9 feet, and used it to process many points on the building itself. Now this kind of capability is really impressive, and so I wanted to show you what could potentially be done with this data. Now, that building is not what the coastal Louisiana looks like. It does not resemble San Francisco. So I'm going to talk about the limitations and what you would have to do in order to use InSAR in the coastal Louisiana area. Next slide. So this is an animation up at the right that kind of goes along with what I'm going to talk about. You collect one image the first time, you measure the amplitude and phase of the backscattered signal. Next click, please. Then you come through again, you collect another image, and you measure the change you measure a new amplitude and phase from the return. And if the surface has changed, like here the surface moved, it actually subsided in a hole, and you see something in the line of sight direction, then that phase change is directly proportional to the change in distance to the ground in the line of sight direction. So for subsidence, you would see a fraction of the vertical change depending upon the line of sight direction that you're looking in from the radar. And that is usually, say, 30 to 45 degrees from a satellite-based instrument. So just to kind of highlight what you could do in an area that is along the San Andreas Fault in California, a black square will show up, and I'd like you to keep your eyes on that while I show you what interferometry gives you in that region. So go to the next slide. And now you see an interferogram, which shows a number of different slow creek landslides across that landscape. They are driven partly by the movement along the San Andreas Fault, and of course exacerbated by rainfall. We get a lot of atmospheric rivers which dump a lot of rain in that area. So it's extremely useful in some of these bare earth areas and uninhabited areas. Next slide. So synthetic aperture radar comes in many different flavors, and those flavors depend upon the frequency at which they are transmitted. So the wavelength for an X-band radar, you'll hear lots of things about the bands of the radar. The X-band radar has a wavelength that's about 1 inch. And so when you think about scattering from an object with radar, you're going to scatter from an object that's about the scale of the wavelength or half the wavelength. So that really measures the canopy. It does not penetrate heavy vegetation well. It works great on targets that are hard targets and bare earth situations where the ground is undisturbed. C-band has about twice that wavelength. It's about 2 inches, 5.5 centimeters, 6 centimeters. It kind of, penetrates the canopy. You get some canopy scattering. You get some scattering from the branches, and so we call that volume scattering. So it definitely can penetrate sparse vegetation. However, you'll get some attenuation of the signal whenever you have heavy vegetation. And then you go to L-band, which is a 24 centimeter wavelength, so 10 inches. That is really best for measuring below trees and through dense vegetation. Just basically passes through the canopy and it sees the structure of large trees, and it penetrates vegetation to scatter from the ground below. Now, you will get some contribution, but in general, it's much, much better because of that long wavelength. So next slide. So people sometimes confuse the information you get from InSAR with what you might get from lidar. Now, an optical instrument's going to measure color. And over there on the right, did you go to the next slide? On the right, it shows lidar, and lidar.
The back one, Randy.
Okay, lidar, you penetrate through. You'll get a waveform scattered back from both the branches and the top of the canopy and the ground. So you're really measuring surface elevation there, or elevation of the canopy height, or elevation of the branches. But if you have moderate vegetation, you're really measuring surface elevation directly. InSAR, on the other hand, measures change in surface position. So it doesn't measure elevation, and it's along the line of sight direction. And it's usually side-looking, so it's a mixture of horizontal and vertical movement if you have both of those at the site. So in this slide, L-band is highlighted with red, so you see it, scattering through to bounce back scatter from the ground. And just to show you a practical implementation within the Louisiana environment, go to the next slide, please. You can see measurements that we made of precursory ground movement before collapse of the bayou sinkhole. Now, this area is definitely like what we're going to be using InSAR to do. The reason that we got this beautiful signal, which is shown at the top, the InSAR map showing this movement before the cavern collapse, was that we used an L-band radar, and we had double bounce scatter from the surface below the trees. So that made this measurement possible. Now, that kidney bean shape is actually a perfect example of the line of sight measurement. The actual deformation was inflow along radial directions into a hole at the center. But because we only measure the component in the line of sight direction, the horizontal movement that was perpendicular to our beam on the ground gave back no signal. So this kidney bean, was actually pattern was a sign of radial inflow at this area. So next slide. Another challenge for InSAR is what we call a loss of temporal coherence. And what it practically means is that InSAR does not work everywhere or all the time. If you look at the example on the left, then what it's trying to show is that the backscatter signal that you get is the sum of all of these returns from everything inside of a resolution cell. And a resolution cell for that TerraSAR-X instrument was about 3 feet by 3 feet. For a Sentinel-1, it's going to be more like 60 feet by 60 feet. So there's a lot of structure within those things, and you're summing all of those in a phase coherent wave kind of motion way. Now, if you look at the next figure over to the right, what happens is that if the surface is undisturbed, but it moves as a block, then there's no loss of phase coherence. You really get that relationship that I talked about where the phase change relates directly to the amount of movement that occurred in the line of sight direction. Now, as you get changes in the surface roughness, which is the next panel over, then, you get some change in the phase because things changed on the surface over that time. And basically this adds noise to your InSAR measurement of the surface displacement. You're not able to make quite as clean a measurement as you could before. And one way to get around that is to measure a series of images so that the noise, the real signal adds coherently, and the noise is added incoherently and reduced by the square root of the number of observations that you make. And then on the final panel is the one that we really worry about, which is when you get total change in the surface. The roughness changes a whole lot, and there, the phase noise is just so great that you can't measure that surface movement anymore. the phase is randomized and you just can't relate it to what you had before. And a perfect example of this is open water. Open water is perfectly incoherent because it has, first of all, it's relatively flat, and so most of the radiation bounces forward, so you get very little backscatter. And what backscatter you get depends upon the roughness of the surface. And so the wind causes the water to have little ripples on them. Those ripples change on the time scale of seconds. So your surface roughness changes all the time. Now, for land, these longer wavelength radars are less impacted by temporal decorrelation because that wavelength is longer, and so phase noise is smaller for a given change in distance on the ground or roughness from that little cell. So the next one, please. So just to summarize the takeaways, for InSAR, you use it for measuring surface displacement and deformation. You can use the fact that it's become incoherent to measure a place where something has changed dramatically. So you could tell, for example, maybe where the vegetation was totally inundated, you would get total decorrelation in that case between the first time you did the imaging and the second time. Second takeaway, only the relative change in surface location is detected, not the surface height. Only the change in the line of sight direction is detected. It doesn't work everywhere. For example, open water, where you have major changes in vegetation or soil moisture. And then last, which is really important for our collaboration with LSU, is that the measurements are relative in both space and time. In time, you're taking two measurements, so you're measuring how much displacement occurred between those two times. So you have to collect a long time series of images in order to reduce the noise, the error bars, and if you have very small changes in the surface. So I would call a few millimeters a year of subsidence a very small change. You will need to take measurements for many years, many scenes, in order to measure that with high accuracy. And secondly, it's relative in space. It's a displacement difference between two scene points in the image. So if you want to put it in a geodetic frame, you have to tie to a location in the image that has no movement or known movement. And then you can back it out and put it in a geodetic frame. So you need those geodetic control points, GPS, anything, and that's why we are interested in working with the Center for Geoinformatics. So next slide. Just to summarize, the goals and the challenges of this project, as I've kind of motivated, it's going to be very challenging to measure subsidence in Louisiana's wetlands, but also in agricultural areas, because you have surface roughness changes from plowing, you have maybe you have a lot of rainfall. Guess what? Yeah, those kinds of things happen, so it's going to be hard. So what we are trying to do at JPL is to use InSAR and determine where it's going to be able to give good measurements of subsidence in coastal Louisiana. And then second, let C4G know where to focus their geodetic control to expand that utility by giving control points. The other thing is, now after I thought of this, after listening to the last speaker, which is that it also tells you where you need to put instruments in order to measure subsidence, where InSAR is probably not going to be able to work at all. So this is very useful for the work that's being done at LSU. Next slide. There is one little wrinkle. It's a particular challenge for InSAR in wetlands environments, and that's that you can get very high coherence backscatter either from motion of the land, vertical land motion, or from water level change if you have emergent vegetation. On the right-hand side, you see an image that shows backscattering from water to the leaves of and stems of the plant, and then back to the radar. That kind of signal can be very large. You'll get a phase change, but what you're measuring is the water level change. And so we need to both identify areas where you lose coherence, but also areas where you maintain coherence, but it's because you're looking at water level change. So anyway, it's an interesting wrinkle, and I think that it's a challenge also, and I wanted to bring it up. Next slide. So there are a lot of synthetic aperture radar missions in the past and operational now. If you look at this long list, these are past instruments and instruments in operation. You look at the second column, the lifetime, you can see, there's more than 5, 7, 8 instruments that are operational now. But if you go over to the right-hand column and look at access, you can see most of it is commercial, which means you're going to pay for the data. They're probably not going to be acquiring data everywhere unless you paid for it up front. And people who get access to it for free is really limited to scientists who are doing research on things like volcanoes, basic science research, geoscience research. The exception is highlighted there in red, which is the Sentinel-1 instrument, which is free and open. And that is changing the use of InSAR dramatically by making it available to people everywhere, regardless of their ability to pay for the data sets. So next slide. This instrument has a C-band instrument, so it's kind of midway between your optimal L-band and X-band. They have launched 2 identical satellites, which gives them a repeat imaging capability of 6 days. They launched those in 2014 and 2016. The design life was 7 years, so it should last a little longer than that. But they are also committed to continuing with Sentinel-1 C and D, so they'll launch 2 more satellites. And then when they reach the design lifetime of those 2, they'll launch 2 more. So they want to provide continuity of this data. And in addition, because there's 2 satellites and they've improved, processing capability and things like that, it now images much, I would say more than half of the Earth's surface at 6 or 12-day intervals. It certainly images everywhere on the Earth yearly. But, for what we are doing in Louisiana, you really need that 6 or 12-day interval in order to maintain coherence. So it's got a data set, and if you go to the next slide, they collect data at 12-day intervals on these frames over these areas. And those green dots are the CRIM sites in southern Louisiana. And you can see that they are fully covered by scenes that are regularly collected by Sentinel. So we're processing that data. We've processed all the scenes from 2000 up to 2020, and we've looked at the coherence in order to identify areas where we think we're going to be able to do good measurements. And for starters, we've kind of focused on areas near the CRIM sites because those would be land where the state would have access, and you, in principle, could install geodetic instruments for tie points there. Next slide, please. So this is a map of the coherence that we got from those scenes. This is the mean coherence across the whole time series. It's really a measure of whether InSAR will work. 1 is perfect, so that's the bright areas. You can see New Orleans really well. You see Baton Rouge. You see the cities are very coherent. And you can see, the roads and ways going down into the delta along certain areas. Now, the light gray areas have modest coherence, and so it's not clear whether they will be good or not. Probably the brighter ones in there will have some areas that work, and then the ones that are really dark are very similar to water, and you're just not going to be able to make InSAR work in those areas. So next slide, please. I just set a threshold. I figured out what water looked like. I looked at variability and around both water and low coherence land sites. And if you put that threshold and you say you need a CRIM station within 100 meters of an area where within that 100-meter radius circle around the CRIM site, you have to have greater than 0.35 coherence than the red stations are. And so you can see a lot of the stations just do not maintain enough coherence for you to make a measurement directly at the station. In many cases, you can make good measurements close to the station, and you can see that on the map just by looking at the location of where the CRIM sites are. So the next step that we're going to do is to expand that radius and really try to identify the areas where we are going to be able to make good measurements with InSAR. And let's go to the next slide, please. As part of that, we are contracting with Trey Altamira. Remember, they did the measurement of Millennium Tower, and they will perform InSAR on a subset of this area, an area where it's particularly challenging, but has, like New Orleans, includes New Orleans in it. That's the red outline on the Google Earth map. And we will get measurements of land surface elevation versus time for the locations where the InSAR can be used. And example of that is shown in the maps, the little plots on the right, where you can see a number of measurements during the year showing the change in the surface elevation as a function of time. So that is the end of what I wanted to talk about the project specifically. And now I'm going to talk a little bit about what's on the horizon. NASA is launching their own SAR mission. It's an ambitious Earth observing mission. It's its first mission of this kind to be used for InSAR for land surface deformation measurements. It's a collaboration between NASA and the Indian Space Research Organization. India is supplying an S-band radar, which is 10 centimeters wavelength, and the U.S. is supplying an L-band radar. So it's like best instrument available for doing InSAR. It was supposed to launch in 2022. It's been delayed to 2023 because of the pandemic. It's got a design life that's like 3 to 5 years, but from experience with NASA instruments, the actual lifetime is usually much longer than the design lifetime. And NASA is already planning on a continuation type mission for this. The repeat orbit will be 12 days, so you'll get a measurement of nearly all of the lands of the Earth's land at that 12-day interval, and you can use that for InSAR. And when I say nearly all of the Earth's land, we're missing the poles, the very, very top of the poles, the land at the top in Antarctica and Arctic. So sea ice in the Arctic. And we're also not measuring over the Sahara Desert across that long a time frame. The data is going to be free and open to all. And I forgot to put on this slide, but it's really important. There is going to be developed a product that gives land surface elevation change as a function of time that will also be available freely and openly from this data. So in addition to just getting the interferograms, you will be able to find a land surface change maps also. Those are being developed right now at JPL. So just to give you a scale of, let's see, if you look at that picture of the satellite, you see there's kind of this, it looks like a ladder extending down. No, that's not a ladder. On the next slide, you can see this 40-foot diameter reflector folded up on the top left-hand side, and that structure holds it in place during launch and before it's deployed. When it's deployed, it's pretty impressive. It's the largest reflector NASA has ever built. It's quite something. And right now, NISAR is being assembled in the high bay at JPL. Both instruments have been delivered, and it's underway. Next slide. So NISAR will have a very wide imaging swath, 150 miles swath, and because you have that very wide swath, you're able to get that 12-day repeat with overlap at the equator so that you can image all the land surface with that repeat. We acquire data on both ascending and descending orbits. Because the orbits get closer together at the poles, you'll get between 2 and 5 passes over any particular site on Earth every 12 days. Of course, at higher latitudes, you get a lot more passes. So 12 days is sort of the longest time between images that you'll get for any particular site on Earth. Let's see, next slide. This is an animation showing the measurement technique. It's actually very difficult to get a 240 wide swath and measure the backscatter. And so it's got a very complicated method for doing that, where it illuminates the entire swath on transmit, but then on receive, it kind of cycles through the transmit-receive modules, so it samples the return in little tiny segments that correspond to the time when it would be returning from scattering from the Earth's surface. So I'll just keep this animation here, and if you're interested in it, you can look it up online. There's information about SweetSAR. The next slide. So that's the conclusion of my slide. I think we are extremely supportive of C4G's efforts in modernization of the NSRS and are very excited to use InSAR for this. We understand that it's going to be challenging, and so we want to really set up so that when NISAR launches, and even before with Sentinel, we'll be able to use, make it more capable, make InSAR more capable in that area. So this C4G is going to use this to tell where to deploy resources to areas where it can help InSAR be successful. And I just want to close by saying that NASA does a total assessment of all its priorities every 10 years. And in the last assessment of priorities, which is called the Decadal Survey, the measurement of coastal subsidence was given the highest priority. So this is extremely important to NASA too. So I'm done there. I hope that this has been clear, and I'm happy to take questions.
Thank you very much, Kathleen. This is Tony speaking. I have a couple of questions. One I answered from our point of view, but I'm going to pose it to you as well. Are you installing InSAR reflectors in areas where you don't get good coherence? My answer was it's something we're hoping to study and perfect.
Yeah, JPL is not doing that, and NASA is not doing that. It would be something that one of the agencies would do. Is that your question?
I think so. It's something that here at C4G we've talked about for several years.
Mm-hmm. Yeah.
The second, and in fact, it seems to me that if we find appropriate remote locations that a GNSS antenna matched or attached firmly with a reflector would provide you the temporal change in data that you need.
Yes, now we don't even need the reflector unless InSAR would not work in that area. Then you would...
We're assuming the area did not work.
Yeah.
All right, and the second question is, oh, I'm sorry, go ahead.
I was going to say L-band reflectors are very large. They're about 6 foot on a side. So you will have challenges other than just installing them. Like they will subside differently than the ground around them, for example, because of their weight.
Yes.
So you'd have to really work on that.
Some innovation.
Innovation.
The second question is, do you use vertical velocities from cores to validate the InSAR-derived velocities?
Absolutely. Everyone needs that data. That's the only way that we are sure that we've taken out any artifacts from the data. It's absolutely essential that we have that kind of data.
All right. Well, thank you, Kathleen. I don't see any other questions or comments.
Well, Kathleen, I have some questions.
George?
For you. This is George Voyages, and I'm interested to know if you can look at the non-floating oil rigs, the ones which are firmly tightened to the floor. Can you get some idea of subsidence for these oil rigs?
Oh, yes. They'll be very bright. Definitely.
Can you provide us that information?
Yeah. If we have the images for that, yeah.
Okay.
We would have to make a special water mask that didn't mask them out, because we apply water masks so that to speed up the processing. That is possible.
Well, the companies that have most of these oil rigs do not allow us to go and put our instruments on the oil rigs, but using InSAR would not be a problem. No one is asking them for permission. We just take the pictures and the echoes and get the information. So that would be great. And the other question is, can you get marine landslides under the sea in the vicinity of our coast?
No, it does. It scatters from the water surface, the very surface.
There's no way. There's no way. Expertise that we can put there to allow us to do that.
Not with InSAR. You might be able to use water penetrating lidar for bathymetry. That's possible in some of the shallower coastal areas.
Well, I really would like to follow in the future on this offshore oil rigs, if we can get some, subsidence for those rigs. It doesn't have to be many, just one or two will be fine. If we can have, a history of those subsidence for the one or two oil rigs.
Yes, yes.
Okay, and we have one that we had instrumented it in the past. I think Randy knows about it. Maybe we can be very specific and ask you for that one.
Okay, I can see whether they collected data over it. They don't collect a lot of data over the ocean, but if it's close enough to the shore, then they can collect it. And actually, NISAR plans to collect the entire Gulf of Mexico all the time to facilitate using that data to look for oil spills.
I see. Okay, and what do they collect? I mean, only for the oil rigs, or just see if there are patches of oil, floating?
It's we would image the entire Gulf of Mexico. The water in the Gulf of Mexico on every pass. So a 12-day repeat image of that area, even out in the middle of the Gulf of Mexico.
Well, thank you, Kathleen.
All right. Thank you, George. That was very informative, and I look forward to some more collaboration between us.